we're going to work on this quantity discount model today. And in this new situations, I'm going to use an example to explain what do I mean quantity discount model and how does that affect our optimal quantity to achieve minimal cost. So bear one thing in mind, that what we're doing here is to try to achieve minimal total cost. Okay, the total cost that we considered in the last class, in the last sessions, was total inventory cost equals to annual holding cost plus annual ordering cost. And this part, these two are actually inventory cost. Now there's a new situation happens, that is, there is a quantity discount. For instance, I'll give you an example. If you order between 1 to 199, the price is $5 a piece. If you order between $200 units to 499 units, then the price is $4.80. Any orders above, including 500, above 500, then the prices are $4.50. So you see that you not only want to optimize your inventory cost now, because you also have enjoy some discount from the quantity, large quantities, possible discount from the large quantities. So now you want inventory cost plus the purchase cost. So, okay, so I'm going to do it here as well. Okay, so this is what you have. And what we're considering is inventory cost plus purchase cost. And we try to minimize total cost. In this case, we do consider the quantity discount. Okay, I can give you an example. You know the quantity discount. Like in the times that I was in the college, I went to we had a soccer team, picked the amateur soccer team, and we tried to get the jerseys. And we went to Sports Authority. Sports Authority, that was an old kind of like a sports, similar to Dick's Sporting Goods, but the Sports Authority is kind of like closed. And it was like at Roseville, and I still remember I went there, that store, and then the next one close to it, it's an electronics store. It is closed as well. It's a Circuit City. It's closed as well. Those two are together, and I went in and I asked the manager for a discount, a quantity discount. You know what? How many quantity we have? Not too much. We only have 15 players. We want a 15 set of jerseys. Still, I was surprised. I was just going to give it a try. The manager agreed to give me he actually gave me a 10% discount. So, even for a small quantity, you can always negotiate, right? So anyway, quantity discount. Right now, we're not only considering the inventory cost, but also the purchase cost. Okay, and our goal here is to achieve minimal total cost. Okay, so starting from here now, I'm gonna have a lot of equations coming out. And now the total cost is carrying cost, which is the holding cost times average inventory level, plus ordering cost, which is S, times frequency of the orders. So this is exactly the same as what we have done before, but we do have the price times demand. Remember, this D here is the demand. With price purchase cost is not the purchase cost times Q. Instead, it's the demand for the whole year. Okay, so this is our new formula to work on, and we try to minimize it. Now, in order to minimize it, we're going to have to have this do the same thing, but it's truncated. It's in 3 different regions. Okay, so okay, so our situation right now is we have a demand for in this example is 1,000 units per year. And the ordering cost is $75 per order. Holding cost is 75% of the purchasing price per year. So 75 times 75% times $5 goes into this one. That is $1.75 per unit per year. Let's give it another try. And for the price, that is $4.80. So times $4.80, $4.80 times 35%. That is the $1.68 per unit per year. That's the holding cost. The same thing goes for the third scenario. That is order quantity that is bigger than 500, and this price per unit is $4.50. So the holding cost is 35% of it. It's $1.58. Now, you see that we have, if we copy our equation over from the past page, so we're gonna copy it over and leave it right here, so easy for us to see. You see that for each one, for each of this one matters. There's something that changes over time. That is, one thing is the H. So for each different the quantity range, your H changes and the price per unit changes. Okay, so we're going to have different equations, total cost for different ranges of the quantities. So we actually have 3 of them, and we have to work out 3 of them. Okay. Okay, now we're going to have 3 scenarios and 3 different equations. Okay, the first scenario is the quantity is between 1 and 199. The price here is 5. Holding cost is 175. Second scenario is quantity is between 200 and 499, and the price and the holding costs are different as well from the first scenario. Third scenario is quantity is between 500 and above 500, and the price is 450. Holding cost is 1.58 per unit per year. So each of them going to have its own total cost, and I'm going to write it here. So here H is 1.75 times Q that we don't know, divide by 2, plus S is 75. Okay, S equals to $75 per order, times D is 1,000, that we know. Let me double check. The demand is 1,000 units per year, divide by Q, plus P is 5, times demand is, let me make it formal, times demand is 1,000. So can I somehow, okay, so I'm gonna consolidate a tiny bit, 1.75 Q divided by 2, so I'll leave this, and it's 75,000 divided by Q plus 5,000. Okay, so that is this equation. Let's look at the second equation here. So this one, H is holding cost. H holding cost is different. So 1.68 times Q divided by 2 plus S. S equals to 75. So S does not change it. 75 times 1,000 is the demand divided by Q plus price. Price is 4.8. 4.80 times 1,000. So I'm going to also consolidate a little bit. So 1.68 Q. I leave this. No. Yeah. Okay. So about 500. Oh, oops. I'm going to have to copy this equation. So this one here. Now, S equals to 75 as well. Holding is 1.75. So this one goes to here. Times Q divided by 2 plus S 75 times 1,000 divided by Q plus P price. Price is 4.5 times 1,000. And it's 1.58 Q divided by 2. I just try to make it cleaner to see it. Okay. And so this is the third equation. We have 3 different equations. Each one has its own region, and we have to work on it. Okay. Now, I'm going to have a separate slide to work out the minimization of this for you. Okay, so the total cost here is H times Q divided by 2 plus S times D divided by Q plus P times D. Now we're going to remember our condition to achieve minimal TC. Remember there's 2 conditions. Okay, the first derivative equals to 0. Second derivative bigger than 0. So what happens is, in which case we had a curve looks like this. First derivative makes sure you reaches the minimal. Second derivative is bigger than 0. Make sure the curve is it's like facing up instead of like this. This one is still the first derivative. The maximum first derivative goes to 0 as well, but for this one, the second derivative actually is smaller than 0, and this one is the first derivative bigger than 0. Okay, but you don't have to really memorize all this. Just remember, we actually, when we solve this, we needed these 2 conditions. Okay, now we're going to solve this, and we're going to find out something surprisingly friendly. So for this one, we take the first derivative, right? So we take first derivative looks like this first. Okay, we wanted it to be equals to 0, and the first derivative equals to 0. So we set the first derivative equals to 0, and the first derivative actually is very interesting because you see first derivative equals to the derivative of this part on Q plus PD on Q. Take a derivative. Okay, so let me do a better writing here. So the interesting part is this is exactly same as what we've done before. And this part, P and D has nothing to do with Q. So P and D are constants when we take this derivative on Q, P and D can be considered as constant. So this part equals to 0. Okay, so this is a little nuances about calculus. So if you don't want to memorize it, it's okay. So this part is 0, and this part is exactly same as what we have done before. So this part is let me write cleaner notes for you. And we set it equals to 0. You know what? We solve this for Q. And we find that Q star is exactly same as before. So if this one is exactly same as before, then we know that the second derivative, I'm going to skip that. We know that. I'll just tell you that second derivative. If you take a derivative of this part again on Q, and it's always positive. So the second derivative is actually always positive. So we know that I'm going to skip that part, the proof part. Instead, we're going to focus on our work. So we know that the interesting part is our Q star is exactly same as before. It's 2ds divided by h. Take a square root. Okay. All right. So I'm going to write it here. Q star is equals to 2ds divided by h. And here's the total cost. So we're first going to find out the Q star, and we're going to draw the curve here. Okay, so Q star here equals to 2ds divided by h equals to 2 times demand is 1,000 times s 75, which is the ordering cost, divided by h. H here is the holding cost is 1.68. Okay, so this is the middle one. Let's look at the first one. Where's our first one? First one is here. First part is quantity between 1 to 199. And this Q star actually, so Q star equals to 2ds divided by h as well. And so we're going to calculate Q star here is 2ds divided by h, which is 2 times D is 1,000 times S is $1.75 per unit per year. Divide, S, I'm sorry. The S is not 1.75. Here, the S is $75 per order. Divided by H is 1.75. Okay. If you do this calculation here, and you're going to have a result of the EOQ here, which is 292.77, because we cannot order, fraction of units. So roughly, we're just saying, all right, so 293. We do the same thing for the next, which is Q between quantity between 200 and 499. And this Q star here equals to 298.81. And roughly it's 299 units. That's the optimal. And the third one is, again, Q star equals to 2ds divided by h here. And here Q star equals to 2ds divided by h equals to 2 times D is 1,000 S is $75. H is the one that is different. H here is the holding cost per unit per year, so 1.58. So if we finish this calculation, we find that this Q star equals to 308.61, roughly it's 309 units. Okay, so we have three different scenarios here. First scenario, Q star is 293. Second scenario, for the first scenario, when the Q is between 1 to 199, which is the quantity less or equal to 199 units, the best Q star is 293. All right. So let's look at it. So the curve here right now, this is our total cost line, and this is the Q, right? And then our total cost line gonna be like this, and it go down because from here, this is a 199. Above 199, it doesn't exist, right? Because our Q is between 1 to 199, and the optimal Q star actually, so our Q actually goes, I have to extend the Q here. Okay, so the optimal actually is right here, is 293 units. The optimal, according to our calculation, EOQ calculation, does not exist. It's not feasible. So our cost between total cost here, we can observe by looking at the line here, and we see that before 293 units, the cost keeps decreasing when the Q increases. Okay, so I'm going to write it here. Before Q equals to 293, total cost decreases when Q increases. Right? If you look at the curve here, that is the total cost curve, and it decreases. And so we know that the minimal total cost here happens when Q equals to 199. Because it decreases all the way to 199 and it stops. It doesn't exist anymore. So this one is our total cost, is Q equals to 199. All right. So if we plug in Q equals to 199 into this equation, so then we have this TC equals to, I'm going to have a really small space here. So I had to be careful here. And what is that cost? All right, so if we finish this calculation, we have this roughly equals to, and plug in Q equals to 199 here. So Q equals to 199 here and here. Okay, so when we finish this calculation, we find it's roughly 6251, and that's this point, that's this TC. 6251. Remember this, we're gonna need this later on, okay? And then we're gonna do the second one. The second one is right here. So we're gonna have a curve, again, total cost. So I'm gonna have to be careful with this space here. I have limited space. This one here is between, remember, it's between 200 and the units possible quantity is between 200 and 499. And the minimal is 299. So we can imagine that from here is 200, from here is 299, And we're going to have a curve that's the real one, that's at the bottom, and the rest goes up. But dashed lines means it's not real. The middle part is real. Why it's real? Because we know 299 is somewhere in the middle, gives you the minimal, and it's feasible because this 299 is feasible because it's in between 200 and 499. Okay, so this one is feasible. So we have this Q star here that is 299, and our total cost, I'm going to copy it over from here, is plug in the number 299. And if we finish the calculation, we find that the total cost is 5052. It's right here, 5052. Okay, we do the same thing for the quantity that is bigger than 500. So for the quantity that is bigger than 500, we have the Q equals to 309. And if we look at it, our curve looks like this. Again, it's always like this, right? And but it's not really like this, because before 500, it's dashed line. Only after 500, it becomes a solid. It becomes real. Before 500, it's not feasible. Now, however, according to our calculation, our Q star wanted to be somewhere at the 309. 309 is not feasible. Okay, and we know that the minimal is the 309. After 309, total cost increase as Q increases. Now, we don't want it to increase. We want it to be, we want a minimal total cost. So our minimal total cost can be achieved when Q equals to the lowest point here, which is 500. Okay, now we can plug in the 500 to the total cost equation. And the total cost equation here equals to 1.58 times Q divided by 2. Okay, plus 75,000 divided by Q plus 4,500 equals to 1.58 times 500 divided by 2 plus 75,000 divided by 500 plus 4,500. And if we finish the calculation here, we find that this Q here, when Q equals to 500, give us the minimal total cost for the large quantity discount scenario here. And our total cost equals to rough 4,651 when Q equals to 500. Now, we put them together. We see there's a 3-part of the line, which we shaded it, highlighted in like thick red area. That is our 3 feasible lines. And the first one, we know that the total cost achieved at Q equals to 199. And we know that the number is 199. Where is it? 199. Q equals to 199 is 6251. Okay, this is the first between 1 to 199, that's the first minimal Q, 6251. The second one is between the Q between 200 and 499 is 5052. So between 200 and 499, the total cost achieved here is Q equals to 299.5052. Okay, the third one is here. The third line is the total cost equals to, the price is 4.5. This is price 4.5 unit per unit. This is the pink one is the price 4.8 per unit. And this top one, the blue one, is priced at $5 per unit. And for this one, we can find that the minimal Q achieved at Q equals to minimal total cost can be achieved at Q equals to 500. So TC when Q equals to 500. And the total cost is 4651. 4651. Okay, I'm gonna move this a little bit to here. Okay. 5052. Let me clean up. So it's not all crowded in a small space. Now we can achieve three different kind of total costs. And so the price range between, the quantity range between 1 and 199, the minimal total cost we can achieve is 6251, $6,251 when Q equals to 199. When in between the quantity between 200 and 499, what we can achieve with the minimal total cost is $5,052. And when Q is above 500 in this kind of curve here, in this kind of range, when the quantity is bigger than 500, we can achieve the minimal total cost when Q equals to 500. So you see, out of this three, which one is the smallest? The minimal total cost can be achieved is $4,651, where Q equals to 500. And that is the this is our result. It's Q equals to 500. I will share this new exercise to you.